Hi all, today we discuss an example of uh, the theorem, illustrative example of the theorem what we have discussed in the last class, and two important subspaces of the vector space if there is a linear transformation. So first we discuss example. Suppose we have alpha 1 is equal to 1 2 and alpha 2 is equal to 3 4. Okay, our idea is to define a linear transformation which maps this 1 2 2 3 to 1 and this uh, 3 4 to 6 5 4. This is our intention. 6 5 4. That is, if you consider R2 and R3, and this is a basis for uh, R2, and this is two vectors beta 1 and beta 2 come from this R3. Then construct T such that T of alpha 1 is equal to beta 1 and T of alpha 2 is equal to beta 2. This is what we have to discuss. How will you find the linear transformation satisfying this? So the idea is, if you have xy, an arbitrary xy belongs to R2. To define linear transformation means find the image of this arbitrary element x comma y. So first you write this xy. Since xy is an element of R2, this can be written as C1 times 1 2 plus C2 times 3 4. That is equal to C1 plus 3C2 comma 2C1 plus 4C2. Okay, these are the components of the sum. So that should be coincident with this xy. So we have two equations: c1 plus 3c2 equal to xy x, and 2c1 plus 4c2 is equal to y. When you subtract by multiplying this with 2, you can write it as 6 here, and this is 2. Then subtract, then you can get, or subtract the second equation from the first. You can get 2c2 is equal to 2x minus y. Then c2 is equal to 2x minus y divided by 2. Then our equation was c1 plus 3c2 is equal to x, and 2c1 plus 4c2 is equal to y. When you divide the or multiply the last equation by 1 by 2, when we multiply it by 1 by 2, you can get c1 plus 2c2 equal to y by 2, and the first equation is c1 plus 3c2 is equal to x. Now by subtracting this, you can get the same. Oh, that is c2 again. That is c2 is 2x. 2x minus y by 2. In order to get the C1, you need to equate the coefficient of the second component, second variable. That is, I'll write once again. If you replace this as 2, and this is our equation. So just forgot this one. We don't want to that again. This is by multiplying this with 4 and multiplying this with 3, you can get two new equations: 4c1 plus 12c2 equal to 4x, and here we have 6c1 plus 12 c2 is equal to 3y. Then by subtracting this, you can get this minus 2c1 is equal to 4x minus 3y. Then c1 is equal to 3y minus 4x divided by 2. So these are the values of the c1 and c2. This shows that whenever you write xy in terms of 1 2 and 3 4, you can get the coefficients. First one is 2x minus y by 2, and this times 1 2 and 3. This is our C2, right? So we write C1 here. C1 as 3y minus 4x by 2, and C2 we have 2x minus y by 2 times 3 4. Okay, now define t of xy. T of xy as since t is linear, the t of this quantity is equal to 3y minus 4x by 2 times t of 1 2. So t of 1 2 should be coincided with this 3 to 1. So write it as 3 to 1, that is t of 1 2, and this times t 2x minus y by 2 into t of 3 4, that is t of alpha 2 should be constant with 654, that is 654. Okay, so this is equal to 3 times this plus 6 times this. Okay, so when you simplify this, you can get the first component is 3y by 2, and the second component is 2x plus y by 2 and 4x minus y by 2. Okay, 4x minus whole divided by 2. This is also 2x plus y whole divided by 2. So this is the explicit form of t of xy. So this will be unique. So once you fix this beta 1, beta 2, and alpha 1, alpha 2, you can get a finite, you can get a unique t of xy in this manner. Okay. Now, in order to find the value of t of 1 0, t of any vector other than these two, you can use the same argument. You write t of 1 0 as a linear combination of some c1 times 1 2 and c3 times c2 times 3 4. Then this will be c1 times t of 1 2 plus c2 times t of 3 4. But we know that this c1 times t of 1 2 is 3 to 1 plus c2 times t of 3 4 should be 6 5 4. So in order to get the image of 1 0 under this t, we need to find out c1 and c2. If c1 is this one, then you can get c1 is equal to in this case x equal to 1 and y equal to 0. So x equal to 1 and y equal to 0, we can get this as minus 2, and c2 is x equal to 1 again, y equal to 0, that is 1. So by substituting this minus 1 times, this is not minus 1, 1 times, sorry, minus 2 times, that is c1, 3 to 1 plus 1 times 6 4 4, that is equal to minus 6 minus 4 minus 2 plus 6 5 4, that is equal to 0, minus 4 plus 5, that is 1, and minus 2 plus 4 is 2. So this is the image of 1 0 under this transformation. So without finding the explicit formula of this t of xy, you can easily find this t of 1 0 using these coefficients. So these are the important as far as this t is concerned. Okay, now we will discuss two important subspaces connecting linear transformation. To define a linear transformation from V to W, these two vector spaces should be defined over a common field F. Okay, so if this is the case, we define two interesting subsets of this T, subsets of this V using this T. So first one is N. N consists of set of all alpha belongs to V such that T alpha is equal to 0, and next is R. R is defined as set of all beta belongs to W such that beta is equal to T alpha for some alpha. Some alpha belongs to V. So these are the two important subsets of this is a subset of V, and this is a subset of V, and this is always a subset of W. So these are the important subset regarding this T. Now, first we consider this. When you take a linear transformation, then t of 0 can be written as t of 0 plus 0, that is equal to t of 0 plus t of 0. This t of 0 are elements of is an element of the vector space W. Therefore, this by cancelling this or writing like this, you can write t of 0 is equal to 0, implies 0 is always an element of n. That means additive identity of the vector space V is always an element of this set. Okay. Now we call the we take any two element alpha comma beta belongs to n. Then t alpha equal to 0 and t beta is equal to 0. Consequently, what is the image of t of c alpha plus beta? That is c times t alpha plus t beta, that is equal to c times 0 plus 0, that is equal to 0. This shows that whenever alpha comma beta belongs to n, then c alpha plus beta belongs to n. That is, this n is a subspace of V, and it is called null space of T. Okay. So null space of T is always a subspace of V, and it is defined as this set. So in order to distinguish this is the null space of T, we write NT instead of N. Okay. NT is a null space of this linear transformation T. Then NT is always a subspace of the vector space V. Now we consider this set. This consists of set of all images of elements of alpha and elements of V under this T. So once you take this set, and we know that 0 is equal to T of 0. Therefore, this 0 is an element of W, and this 0 is an element of V. Okay, so image of this 0 is the 0 in W, then this is always in this set. Okay, because this 0 can be written as image of some element. So R is always a non-empty subset here, non-empty subset of W. And if you choose any two element, say beta 1 and beta 2 belongs to R, then you can get beta 1 is equal to T of alpha 1 for some alpha 1, and beta 2 is equal to T of alpha 2 for some alpha 2 belongs to V. Now you consider C beta 1 plus beta 2, that is the linear combination of these two elements. Then that can be written as C times T alpha 1 plus T alpha 2. Consequently, this will be equal to T times C alpha 1 plus alpha 2, because T is linear. Okay, so this shows that this is an element of R, because C beta 1 plus beta 2 is an image of C alpha 1 plus alpha 2, and this is also an element of V. So we can say that this is an element of R. So that is, R is a subspace of W, and this subspace is called range of T. So range of T, as far as this linear transformation T is concerned, two important subspaces are there. One is a subspace of V, and another is subspace of W, and the subspace defined in this manner is called range of T, and it is in fact this is defined this is denoted by RT. So first we have proved RT is non-empty, and RT is a subspace of this vector space W. So if you are given a linear transformation T, then you can get two important subspaces. One is null space of T, and next is range of T. Okay, so the null space of T is the set of all vectors alpha in V such that T alpha equals 0. Similarly, the range of T is set of all images of elements of V under this T. And two important definitions regarding this is the dimension of null space, that is denoted by null NT, that is called nullity of T. Nullity of T. Similarly, the dimension of RT, that is range of T, that is called rank of T. So we can define two important characteristics of the linear transformation. One is nullity of T, and next is rank of T. So rank of T is defined as the dimension of range of T, range T, and nullity of T is defined as dimension of null space of T. Okay, these are the two important subspaces and definitions. Next class we will discuss two important theorems regarding this linear transformation.